You ever look at a spreadsheet, a table of numbers, and just feel like there's a secret story hidden in there somewhere? Well, today, we're cracking the code. We're going to find that secret pattern, the slope, that's hiding in a simple table of numbers, all without ever having to draw a graph.
So here's our game plan for today. First, we'll learn how to spot those patterns hiding in plain sight. Then, we'll learn a really cool trick called the delta method to decode them. We'll put it into action, learn how to dodge some common traps, and finally, we'll see how this whole thing connects to something we can all relate to, a paycheck.
All right, first up, patterns in plain sight. Think of this like a puzzle. Every table of numbers is telling a story about how two things are connected, and our job is to be the detective and find that secret connection. So, this is the central question we're tackling. When all you've got is a table of data, just a list of numbers, and no picture, no graph, how in the world do you find that hidden rate of change, that slope that connects all the dots?
Okay, so a table like this one is really just a list of coordinates on a map. When x is 1, y is 5. When x moves to 2, y goes to 7, and so on. Our mission, should we choose to accept it, is to find the consistent pattern, the rate of change between these points.
Now, to find that rate, we need a special tool. And yeah, it sounds a little fancy, but the delta method is actually a super simple, super powerful key that unlocks this entire puzzle.
Let's just be crystal clear on what we're even looking for. Slope is just a number. That's it. It tells us how much the y value goes up or down every single time the x value takes one step forward. It's basically the line's signature move. And this right here, this is our master key. All we have to do is find the change in that y column and divide it by the change in the x column. That's it. That is the entire formula. Simple, right? Let's put this key to use. As x jumps from 1 to 2, right? That's a change of +1. And at the exact same time, y jumps from 5 to 7, that's a change of +2. Now that little triangle symbol you see, that's just a Greek letter delta. It's just math speak for change in. So we take the change in y, which is 2, and we divide it by the change in x, which is 1. Our slope is 2.
Okay, theory is one thing, but let's see this thing work in the wild. We're going to put the delta method to the test by solving a few different cases. We'll start easy and then get a little bit trickier.
Let's start with a nice, clean example. In this table, you can see the x values are stepping up perfectly one by one, 0, 1, 2, 3. This is pretty much the most straightforward case you're ever going to see.
So let's apply our steps. First, the change in y. As we go from 4 to 7, that's a jump of +3. Easy enough. Next, the change in x. As we go from 0 to 1, that's a jump of +1. And the final step? You know it. We divide.
So, with a change in y of 3 and a change in x of 1, our formula tells us the slope is just 3 divided by 1, which, of course, gives us a final answer of 3. And that is the secret pattern for this entire table.
All right, case 2. Now things get a little more interesting. I want you to notice two things here. First, the y values are actually going down. And second, the x values aren't just jumping by 1 anymore. See that? They're jumping by 2.
Let's apply our method. The change in y from 20 down to 14 is a change of -6. The change in x from 2 up to 4 is a change of +2. Time to divide.
Let's do the math. The change in y, -6, divided by the change in x, +2, gives us a slope of -3. And that negative sign is really important. It's the clue telling us this line is heading downhill.
For our last case, we've got a different kind of question. The question is, are these points even on the same line? For that to be true, the slope, that rate of change, has to be the same between every single pair of points. It has to be constant. Time to investigate. Let's look at our first jump, from point 1, 2 to 3, 6. Y changes by 4, and x changes by 2. Okay, 4 divided by 2 gives us a slope of 2. Now let's check the next jump. Y goes up by 4 times again, and x goes up by 2 times again. The slope is still 2. Because that rate of change is constant, we can confirm, case closed, this is a straight line.
Now that we have the method down, let's cover the common mistakes that can trip up even the best pattern detectives. I always say, knowing the traps is the best way to avoid them.
All right, listen up because this is important. There are two very common traps that are super easy to fall into, so let's make sure we know exactly how to spot them. Okay, so here's the deal. First, don't get lazy and only look at the y column. That shortcut only works if x is stepping perfectly by 1. You have to check the change on the x side. Second, if you calculate the slope between 2 points and get 2,
But then you check another pair and get 3, it means one of two things. Either you made a small math error, or those points just don't form a straight line.
Okay, we've solved the puzzles, and we've avoided the traps. Now let's see why this skill is actually useful outside of a math classroom.
This is the classic question, right? When am I ever going to use this? Well, the truth is, you use this kind of thinking whenever you want to understand how one thing changes in relation to another.
For example, let's talk about a paycheck. Imagine you worked 10 hours and got paid $150. Then the next week, you worked 20 hours and got $300. In this story, hours is your X and pay is your Y.
And here's the real-world payoff. The change in your pay was $150. The change in your hours was 10. So we just divide the change in Y, your pay, by the change in X, your hours, and we get your hourly wage, $15 per hour. That wage is a perfect, real-world example of a slope. So we've seen that understanding slope isn't some weird abstract math concept. It's just about understanding the relationship between numbers. It's the secret language of data, which leaves us with a final question. Now that you know how to look for it, what other patterns are now hiding in plain sight all around you?